Right now, as you're watching this, on the 3rd of August in a lab in Xi'an, China, researchers are running tests on a machine that is quietly rehearsing for one of the strangest engineering projects ever attempted, beaming electricity from orbit down to the surface of the Earth, across a distance greater than 36,000 kilometers. This is not a concept sketch. It is not a thought experiment for some future decade nobody alive will see. Chinese state media confirmed this year that a test satellite is now scheduled to launch by 2028, 2 years ahead of the original plan, and it is the first real step in a program some Chinese scientists have openly compared to the Manhattan Project and the Three Gorges Dam combined into one. Today, we're going to break down exactly how a power plant the length of 10 football fields is supposed to get into space, how it's supposed to send electricity to your house without a single wire, why multiple countries are suddenly racing to do the same thing at the same time, and what could actually go wrong along the way. No hype, no science fiction, just the actual engineering, the actual timeline, and the actual risk. Drop a comment and tell me if you'd trust power beamed down from orbit into your city. If you want more breakdowns like this, subscribe, it's free. And let's go for 5,000 likes on this one. Let's get into it. To understand why this idea is suddenly moving from paper to hardware, you need to understand the one problem it's actually trying to solve. Solar power on the ground has a built-in flaw that no amount of better panels can fix. The sun goes down, clouds roll in, and seasons change, and every single time, the power stops. A solar array in geostationary orbit doesn't have that problem. Above the atmosphere, there is no night, no weather, and no season, which means the same patch of panels sitting on the ground for 8 or 10 hours of usable sunlight a day could theoretically collect sunlight in space for the entire 24-hour cycle at an intensity researchers estimate is around 10 times stronger than what reaches the surface, because none of that light has to fight its way through clouds, dust, or atmosphere to get there. The idea itself isn't new. It was popularized by science fiction writer Isaac Asimov back in 1941 in a short story that imagined exactly this kind of orbital transmission decades before anyone had the rockets to attempt it. NASA studied a version of the concept after the Apollo program, ran the numbers, and quietly shelved it, largely because the cost of lifting that much hardware into orbit made the entire idea financially absurd at the time. What's changed is not the physics. The physics has been sitting there, fully understood, for more than 80 years. What's changed is that the hardware needed to actually build something this size in orbit, and the rockets needed to lift it there affordably, finally exist, or are close enough to existing, that a real construction schedule now makes sense on paper. Here's where the engineering gets genuinely strange, and worth slowing down on, because most people hear solar power in space and picture something simple, like a bigger version of the panels on a rooftop. It isn't that. You can't just launch a solar panel and point it at a house and expect electricity to fall out of the sky. The actual chain has 3 separate stages, and each one is its own engineering problem. First, an enormous array. Collects sunlight, the same basic process as any solar panel, just uninterrupted and far more intense. Second, that collected energy gets converted, not into a wire you could plug something into, but into either microwaves or a tightly focused laser beam. Because you cannot run a physical cable from geostationary orbit down to a receiving station on Earth. Third, that beam has to be aimed with extraordinary precision at a fixed ground station, tracked continuously as the Earth rotates and as atmospheric conditions shift the beam slightly on its way down, then converted back into ordinary usable electricity once it lands. Researchers at Zhejiang University have already built a working, if much smaller version of this entire chain on the ground, using a 75-meter tower to test the full sequence from energy collection to wireless transmission to a moving target. In their most recent public test, the system delivered over 1,000 watts of power across 100 meters with a wireless transmission efficiency above 20%, and separately managed to keep a stable power stream locked onto a drone flying at 30 kilometers an hour from 30 meters away. That number, a little over 1,000 watts, sounds almost unimpressive next to the scale of the final goal, roughly enough to run a household's essential appliances for a few hours. But every large infrastructure project on Earth started as a scaled-down proof that the physics actually works outside a textbook. And this is exactly that stage, the awkward, unglamorous middle step between theory and orbit that rarely makes headlines, but determines whether everything that follows is even possible. Now let's talk about the actual timeline, because this is where the project stops sounding like ambition and starts sounding like a construction schedule with real dates attached to it. The first real hardware goes up in 2028, a test satellite in low Earth orbit generating around 10 kilowatts, barely enough to power a handful of homes, built purely to prove that wireless transmission works from actual orbit, at an altitude of roughly 400 kilometers, rather than a tower on a university campus. That satellite is expected to carry a solar cell array, a microwave transmitting antenna, and a separate low-power laser payload, essentially testing two different transmission methods side by side to see which one performs better once it's actually operating above the atmosphere rather than through it. If that milestone holds, the next step arrives around 2030, a full megawatt-class station, assembled in geostationary orbit over 36,000 kilometers up, where it will stay permanently positioned above one fixed point on Earth rather than orbiting past it every 90 minutes the way a satellite in low orbit would. By 2035, the plan scales that up to 10 megawatts, roughly enough to power a small town continuously. And by 2050, the stated goal is a fully commercial station generating 2 gigawatts, roughly the output of a large nuclear reactor using a solar collection array close to a full kilometer wide, larger than almost any human-made structure ever assembled anywhere, let alone in orbit. Each of those stages depends entirely on the one before it actually working as designed, which is exactly why the 2028 test matters so much more than its tiny power output suggests. A failure at the 10 kilowatt stage doesn't just delay a minor experiment. It calls the entire 30-year roadmap into question because every later stage assumes the wireless transmission problem was genuinely solved at small scale first. None of this happens without a rocket capable of lifting an enormous amount of hardware into orbit in the first place. And this is the part of the story that connects a power plant to China's entire space program at once, rather than treating it as an isolated science project. The 2028 test is expected to fly on the Long March 5B, already a proven vehicle with a payload capacity around 25,000 kilograms. The geostationary phase around 2030 will likely need the newer Long March 10th, currently being developed with China's crewed lunar program in mind, which gives you a sense of how tightly these programs are actually linked behind the scenes, even though they get covered as separate stories. But the long-term build-out, the kilometer-wide station, depends entirely on the Long March 9th, a super heavy rocket still in development that Chinese officials have described as capable of lifting roughly 150 tons to low Earth orbit in a single launch, standing over 100 meters tall. A station of that size can't be built on the ground and lifted in one piece the way a normal satellite is. It has to be assembled in orbit, launch by launch, the same way the International Space Station was pieced together over more than a decade by multiple countries working together, except at a scale several times larger, carrying components not meant for astronauts to live inside, but for a power grid floating permanently above the planet, requiring a level of in-orbit construction and robotic assembly that has never actually been attempted at this size before. It's worth pausing here on something that rarely makes it into the more breathless coverage of this project, which is the question of whether beaming gigawatt-scale energy through the atmosphere is actually safe for anything underneath the beam, intentionally or not. The honest answer is that the microwave frequencies researchers are planning to use are specifically chosen because they sit in a range that passes through the atmosphere with minimal absorption and minimal heating effect, and the intensity at the center of the beam, once spread out across a receiving station potentially several kilometers wide, is designed to sit well below the threshold. Considered hazardous to birds, aircraft, or people who might wander near the edge of a receiving facility, roughly comparable in intensity to standing near a household microwave oven with the door open rather than anything closer to a weapon. That said, this remains one of the least tested parts of the entire concept precisely because nobody has actually operated a beam at gigawatt scale over a populated area for an extended period, and every serious engineering paper on the subject treats beam safety, precision targeting, and fail-safe shutoff systems as unresolved problems requiring years of additional testing before any full-scale station could realistically be approved to operate near a city rather than in a remote, sparsely populated receiving zone. There's also the economics question sitting underneath all of this, because the physics working in a lab doesn't automatically mean the finished product makes financial sense, and this is genuinely the part of the story that has sunk similar proposals before. Launch costs remain the single biggest line item in any space-based solar proposal, since you're not just launching one satellite. You're launching enough mass, potentially tens of thousands of tons for the full-scale 2050 vision, to assemble something close to a kilometer wide. Even with reusable rockets, driving launch costs down sharply over the past decade. Engineers working on these proposals openly acknowledge that the economics only start to make sense if launch costs keep falling roughly the way they have been, and if the receiving infrastructure on the ground, the antenna fields needed to catch the beam, can be built cheaply enough to compete with simply building more conventional solar farms or nuclear plants. Instead, this is precisely why the current plan is staged rather than attempted all at once, 10 kilowatts, then a megawatt, then 10 megawatts, then 2 gigawatts, because each phase is effectively a checkpoint where the program's backers can look at the real costs so far and decide whether continuing to the next phase still makes financial sense, rather than committing hundreds of billions of dollars up front to a station that might turn out to be uneconomical the moment it's finished. It's worth pausing on why this is happening in China specifically, and not somewhere else, because the honest answer isn't really about the physics at all. Space-based solar power has been technically possible in some form for decades, and the reason it never got built has always come down to two things: an enormous upfront cost with no return for years, sometimes decades, and the kind of sustained, decade-spanning coordination between research institutions, state contractors, and launch providers that private markets generally aren't built to sustain on their own, since no single company wants to fund a 30-year project with no revenue until the very end. China's approach folds research universities like Zidian, its main state aerospace contractor CASC, and its national rocket program into a single coordinated timeline with government-backed funding attached to every phase. The same top-down coordination that let the country build its entire high-speed rail network and its own space station on an unusually compressed schedule compared to how similar projects have typically unfolded elsewhere. The United States explored a version of this concept after the Apollo program and largely let it fade for exactly those reasons: cost and coordination, with NASA's interest diminishing sharply once the immediate space race ended and no clear near-term funding source stepped in to replace it. And it's not just China anymore, which is really the part of this story that turns a single country's ambitious project into an actual global race worth watching closely. It's telling that the renewed interest now showing up elsewhere is arriving specifically in response to China's timeline moving forward rather than independently of it. In the United Kingdom, a government-linked proposal has been floated with a price tag reportedly above $20 billion, aiming to have a working station contributing to the national grid within roughly the same general window China is targeting for its own megawatt scale milestone. Japan, which has quietly run its own space-based solar power research program for decades through its National Space Agency, has recently signaled renewed interest in accelerating its own timeline, rather than letting the concept remain purely academic the way it largely has since the 1980s. The European Space Agency has commissioned its own feasibility studies, examining whether a European-led version of this technology could realistically contribute to the continent's energy security, particularly in the years following disruptions to conventional energy supplies that made energy independence a far more urgent political priority than it had been previously. None of these other efforts currently have anything close to a funded, dated launch schedule the way China's program now does, which is exactly why so much of the current global attention is focused on Xi'an rather than anywhere else. But the fact that multiple governments are now commissioning serious feasibility studies in the same rough window China set its own 2028 date is not a coincidence. It's a direct response to watching one country actually move first. So what does a working version of this actually mean for you, assuming every phase of this timeline holds, which is itself a genuinely large assumption given how many multi-decade infrastructure projects slip, shrink, or quietly get canceled somewhere in the middle? It is not a replacement for the power grid you're plugged into right now, and nobody working on this project is claiming otherwise, no matter how dramatic the framing gets in some of the coverage circulating online. Even the 2035 target of 10 megawatts is a rounding error next to what a mid-sized city actually consumes in a single day, let alone what an entire country consumes. The real significance sits further out at the 2050 stage, where 2 gigawatts of orbital power delivered continuously day and night, regardless of weather, cloud cover, or season, starts to function less like an experiment and more like a genuine addition to a national grid, one immune to the single biggest weakness every ground-based renewable source shares: the fact that the sun simply isn't always shining where you need it to be. Whether that specific promise survives 3 more decades of engineering, setbacks, cost overruns, safety reviews, and geopolitical friction over who gets to point microwave beams at the Earth and where those beams are allowed to land is a separate question entirely, and it's one worth watching far more closely than the more sensational headlines currently give it credit for, because the gap between a working 10-kilowatt test satellite in 2028 and a fully operational 2-gigawatt station in 2050 is enormous, and nearly every space-based megaproject in history has taken longer, cost more, and delivered less than its original announcement promised. There's also a strategic dimension to this that rarely gets discussed alongside the pure engineering story, and it's worth naming directly rather than glossing over. A country that successfully operates orbital power infrastructure doesn't just gain a new energy source, it gains a demonstrated ability to build, launch, and precisely control large, complex structures in orbit at a scale no other nation has previously attempted, along with the underlying rocket capacity in the form of the Long March 9, that doubles as the same class of heavy lift vehicle needed for crewed lunar missions and deep space exploration more broadly. That overlap is not accidental. The same super heavy lift capability being developed to carry solar station components to geostationary orbit is explicitly the same capability China has said it needs to support a crewed lunar program later this decade, which means investment in one program directly accelerates the other, and it's part of why this project deserves attention beyond just the energy angle, since the infrastructure being built to support it has implications stretching well past electricity generation alone. It's also worth naming the skepticism directly, rather than only presenting the optimistic version of this story, because plenty of energy researchers outside China remain genuinely unconvinced this ever becomes cheaper than simply building more solar and wind capacity on the ground. The argument against space-based solar has never really been about whether it can work. The physics was settled long ago. It's about whether it can ever work cheaper than the alternative. And ground-based renewables paired with batteries have gotten dramatically less expensive over the same years China has developed this program. Critics point out that a kilometer-wide station assembled piece by piece over dozens of launches carries fixed costs a solar farm on empty land simply doesn't, and even optimistic launch cost projections may never close that gap. Supporters counter that the comparison misses the point, since the entire value of orbital solar is continuous, weather-independent output that no ground-based system can match, regardless of how cheap panels get, making it a complement to renewables rather than a direct competitor. Neither side of that argument gets settled until real numbers come back from an actual operating station, which is exactly why the 2028 and 2030 milestones matter so much. The honest, grounded summary is this. China has moved a decades-old science fiction concept into an actual construction schedule with a real launch date, a real rocket, and real hardware already tested on the ground, not just modeled on paper. The first satellite goes up in 2028, generating a modest 10 kilowatts purely to prove wireless transmission works from real orbit. The first meaningful orbital power station, if the timeline holds, is assembled by 2030 in geostationary orbit. The system scales to 10 megawatts by 2035. And the final version of this project, a kilometer-wide array beaming 2 gigawatts down to Earth, comparable to a large nuclear plant, is currently targeted for 2050, riding on a rocket that hasn't flown yet, built by a country that has now hit every major space milestone it has publicly set for itself over the past 2 decades, from its own space station to a growing lunar exploration program. Along the way, there are real unresolved questions worth tracking rather than glossing over. Whether beam safety holds up at full scale, whether the economics stay viable as the stations grow larger, and whether the rest of the world's own competing efforts in the UK, Japan, and Europe end up racing China to a working system, or simply watching from a distance as one country builds it first. We're going to keep tracking this as each phase actually happens, sourced straight from the researchers and the space agencies building it, not recycled headlines dressed up as breaking news. Subscribe so you don't miss the 2028 test when it happens, because based on how this program has moved so far, arriving 2 years ahead of its own original schedule already, it's coming faster than most people currently expect. And leave that comment below. Tell me whether you think a project this size actually holds to its own timeline, or whether the 2050 target quietly slips the way most 30-year infrastructure promises eventually do, the way so many ambitious energy projects have slipped before it. Because behind every stage of this timeline is a research team in Xi'an running one more test on a 100-meter tower, a rocket engineer somewhere finishing the design work on an engine that hasn't flown yet, and 3 decades from now if everything actually goes to plan, a receiving station somewhere on Earth quietly pulling electricity out of a beam that started its journey 36,000 kilometers overhead. 5,000 likes on this one. Let's go. See you in the next one.